All right, today we're talking about shapes and how the different Lewis structures exist in 3 dimensions. Okay, so this is called Vsepr or Vsepr. It stands for valence shell electron pair repulsion, and that's the idea. Okay, the idea here is that the bonds and lone pairs of electrons around that central atom are going to repel each other because they're all negative, and they're going to repel each other as far away as they possibly can. So the first thing to do when deciding about what shape is to draw a Lewis structure. Okay, and remember when we did Lewis structures, I said make sure you are good at these because that's the most important part. So if I'm going to draw a Lewis structure of something like CH4, we'll start nice and easy. I would go through my whole process here, count my valence electrons, but I know that CH4 just looks like this. Okay, so CH4 has 4 electron domains around it. Okay, each bond counts as an electron domain. Here's water. Water also has 4 electron domains around it, okay? Because each bond counts as 1, but each lone pair also counts as 1. So a lot of you, when you were trying to draw Lewis structures and you were putting those extra valence electrons on the central atom, you would spread them out, and I said pair them up because it's going to make your life easier, and this is where it's making your life easier. So this has 4 domains of electrons. This also has 4 domains of electrons because a bond counts as a domain, or a bonding area counts as a domain, but what also counts as a domain are those lone pairs, okay? Finally, something like this is formaldehyde. This has 3 domains of electrons. Because this counts as a domain, this counts as a domain, and this double bond counts as 1 domain. There's just 2 bonds in it, so it's 1 area of electrons, okay? Then, that's how you determine your electron domain geometry. You're going to use this sheet for now until you memorize it. Oh, where are you? There you are. Okay, let's do it like this. Move you up, move you up. You're going to use this sheet, and this sheet has some electron domain geometry on it. So the electron domain geometries are the ones that are at the top of each area. So you can have 5 different electron domain geometries. You can have linear, you can have trigonal planar, you can have tetrahedral. Let's see, move you up. You can have trigonal bipyramidal. Or finally, you can have octahedral. Okay? So there's 5 options. And basically, if there are 6 domains around that central atom, it's octahedral. If there are 5 domains around that central atom, it's trigonal bipyramidal. 4 tetrahedral, 3 trigonal planar, and 2 is linear. To figure out your molecular geometry, you need to account for how many of those domains are bonding, have a bond or 2 or 3 in them, versus non-bonding or are a lone pair. So for example, CH4 above has 4 domains, and 0 of them are lone pairs. So its electron domain geometry is tetrahedral, and its molecular geometry is tetrahedral, okay? Whereas water, which we drew above, has 4 electron domains, but 2 of them are lone pairs and 2 of them are bonds. So its electron domain geometry is tetrahedral, but its molecular geometry is down here. It's bent because it's 2 bonds and 2 lone pairs. What I like to kind of explain as the ones that I highlighted here in yellow, those are like the menus. So once you figure out your electron domain geometry, you pick one of those and then you expand it. So it's like there's like a plus sign there, and then you'd expand it and it would expand to these. So your electron domain geometry is that top one, and then your molecular geometry can be any one of those based on the number of bonds and lone pairs there are, okay? PhET has a really good simulation that we did in class. So if you're looking for some extra practice for this, I would go to, okay, yeah, that's great. There we go. Come on. I would go to PhET, and I would look up molecule shapes. And that really shows you, if you Google that, that'll really show you how they come together and how they bond and how they repel and the different, it lets you spin them in 3 dimensions and lets you see in 3D. The other thing you need to know about the sheet is you need to know those bond angles, okay? Now, ooh, lovely. The bond angles that you need to know are the ones that I highlighted in yellow, okay? You need to know that the bond angle for something that's linear is 180. You need to know that the bond angle for something that's trigonal planar is 120. You need to know the bond angle for something that's tetrahedral is 109.5. You can see that really well in the PhET simulation, that it's not, even though it might look like it's 90 when I draw it in 2 dimensions, like this. This looks like a 90-degree angle, but it's not. It's 109.5, because remember, we're in 3 dimensions, okay? You need to know that trigonal bipyramidal is 120 or 90 based on which part of it it is. And you need to know that octahedral is 90, which is down here. There's octahedral is 90, okay? Then you need to know how it changes if there's lone pairs, okay? You need to know how it changes if there's lone pairs. So let me show you an example. We did this one already. We did CH4. So even though that looks like it's 90, it's 109.5, okay? As soon as I replace one of those hydrogens with a lone pair to be like NH3, this lone pair repels those bonds more than the bonds repel the lone pair, okay? They're just a little bit stronger. So they're a little bit stronger. So this bond right here is technically 107.8 or 107.5, depending on what source you're looking at. I don't need you to know that specific number. I just need you to know that it is less than 109.5, okay? Then, if you add another lone pair, okay, this bond angle right there, these lone pairs are repelling them away, are also less than 109.5. It's like 104.5, but I don't need you to know that specifically. The last thing I need you to know about bond angle is that a double bond will behave the same way. So if you think about it, this double bond, there's 4 electrons there, and this bond, there's only 2. So this double bond repels a lot more than the single bond does. Let's see if this, nope, that's not going to do what I wanted to. Okay, so in this case, the bond, let me redraw it because I circled it there. This bond angle, this would be 120 because there's 3 domains, right? But this bond angle is actually a little bit greater than 120. This one is greater than 120. And this one is a little bit less than 120. Just because a double bond repels those bonds more than the single bonds repel back, okay? So that's what you need to know basically about this sheet. We need to talk about hybridization. I will make another separate video on that. I don't think it's actually very long, but the hybridization for each of these is given here. You need to know, and like I said, there's another video that'll explain what hybridization is, but what you need to know is that if the shape is linear, that its hybridization is SP. If the shape electron domain geometry is trigonal planar, then it's SP2. And if the electron domain geometry is tetrahedral, then it's SP3 hybridized, okay? You do not need to know anything about hybridization if you have expanded octets. So what that means is if it's trigonal bipyramidal, you do not need to know anything about hybridization. And if it's octahedral, you do not need to know anything about hybridization. You will not be asked, okay? I'll make another video on hybridization to explain what that means and where it comes from. So hopefully this was helpful. Use that PhET simulation and see those shapes, and you can see how those bonds repel. As long as you have a good Lewis structure, I think you'll be in good shape. Thanks.